Let us start with today's session. So, I welcome all of you for the week 11 live session for the Power System Engineering NPTEL course. I am Gagan Meghna and I am a third year PhD student in Electrical Engineering Department at IIT Bombay. We will be following the same agenda as we have been following in the previous sessions. So we will start with a brief overview of week 11 material and then we will discuss some questions regarding week 11. And if you have any doubt, you can ask in between also. And just to remind you, the assignment 11 deadline, submission deadline is April 10th. So please submit the assignment before April 10th. And you can find the recordings for these live sessions on the on the NPTEL portal. On the left hand side, you can find the problem solving sessions. There you can find the Google Drive link for where all the PDFs for the session as well as the recordings of the live session are available. Let us start with the overview of week 11. So it's a continuation of week 10, which was about the load frequency control. Again, here also we'll continue with the same discussion, the load frequency control, and then we also discuss. Initially, in week 10, we discussed the load frequency control. So let me just write it here. So week 10, we discussed the load frequency control. For an isolated system. With then without control, or we can say uncontrolled mode, in uncontrolled mode, and then with control, so integral control. So single, this was for a single area isolated system. Okay. So this is what we was discussing in week 10, and detailed equation for that was written. So we can write it here. Let us say let us write it. Let us write it for very simple system for non-reheat type of turbine or controlled mode, and we have an integral control here, and here we have 1 by R, which is coming from the governor, the group. Covenant transfer function, then we have turbine transfer function, and then finally we have the generation and load model. Here we have minus delta PL change in load, and this is delta PG. And here we have transfer function for generation load model, we call it TP, Kp upon 1 plus STP. Okay, and this is delta F. This delta goes to 1 by R. And the same integral control goes here. Let us define the states. These are different states. X2, and let us call delta F as X1. So we can easily write equations for each of these. Let us start with X1. So what we can write here, X1 is equals to X2 minus delta PL multiplied by Kp upon 1 plus STP. If we cross multiply, then we'll find X1 plus X1 dot Tp is equals to X2 Kp minus delta PL into Kp. Now X2 into S is equals to X2 dot, which is dx2 by dt. We know that Laplace transform of this d by dt is S. If we ignore if the initial states are all 0. The initial conditions are 0. And if it is integral, then we write x2 by S. Okay. Now we can rearrange them and write that x1 dot is equals to minus x1 divided by Tp plus x2 Kp divided by Tp minus delta PL Kp divided by Tp. Okay. This is x1 dot. But similarly, we can also write for others. We can write x2 is equals to, what is x2? x2 is x3 into 1 by 1 plus st. So this is very easy. We can write x2 plus x2 dot into tt is equals to x3. So x2 dot is equals to minus x2 divided by tt plus x3 divided by tt. Similarly, x3 is equals to x4, this is minus x1 by r multiplied by 1 by 1 plus stg. So we can write x3 plus x3 dot into tg is equals to x4 minus x1 by r. This is equals to x3 dot is equals to minus x1 by rtg minus x3 by tg plus x4 by tg. It's okay. This is correct. Then we can write x4. x4 is equals to minus ki by s into x1. So x4 dot is equals to minus ki into x1. Now we have all these x1 dot, x2 dot, x3 dot, and x4 dot. We can simply write them in the matrix form: x1 dot, x2 dot, x3 dot, and x4 dot. And this you have to write it in the form of x dot is equals to ex plus bu plus gamma p. State transition matrix, U is control transition matrix, and P is disturbance transition. Gamma is disturbance transition matrix. So this matrix will come out to be like this: minus 1 by Tp, Ap by Tp, 0, 0. Here we have x1, x2, x3, x4 plus. So here no, it is uncontrolled mode, so u is 0. This is minus Kp by Tp, 0, 0, 0 into delta PL. This is 0 minus 1 by Tt, 1 by Tt, 0 minus 1 by Rtg, 0 minus 1 by Tg, 1 by Tg minus Ki, 0, 0, 0. Okay. So this is for a single. This is for a single area. In that also only single generator, single isolated generator under uncontrolled mode, and for a non-reheat turbine with non-reheat turbine. So after this we discussed composite frequency response characteristics. So in this, what did we discuss? If there are more than one generator connected in parallel, within an area. In a one area, if there are number of generators connected in parallel, so we will see how the parallel connection of generator helps. It is how that is helpful. So till now we were having only one single unit, and so for a single unit we have output like this. We have more than one, let us say n generators, then it will be something like this. Here we will be having 1 by R1. Here we have 1 by STG, 1 governor. After that it is turbine, 1 by 1 plus STT1, and then this will give some, this is delta PG, and here it is minus delta PL. And after this we have Kp into 1 plus STP. This will give us final delta F. So there will be a single delta F because of all the generators connected in parallel. So this is for the first one. Similarly, we can have the second one also. Here it will be 1 by R2. This will be 1 by R2 minus here. This is U12. That is only U22. This will be 1 by S TG2. This will be 1 by 1 plus S TT2. And this will be delta PG2. Yes. Similarly, you can have last one nth. So it is 1 by Rn. Here it is un 1 by 1 plus s tgn 1 by 1 plus s tt n, and then we have delta pgn. Okay, in this way we have three generators here. So this is multi-unit isolated power system. So let me write it here, multi-unit. It is multi-unit. This was a single unit. Multi-unit isolated power system. After this, we will see how what will happen if two power systems are connected. So there are two areas. Each area is representing one power system, and when these two power systems are integrated together via a tie line or a three-phase transmission line. For this multi-area isolated system, for uncontrolled output, uncontrolled mode, that means U is equals to 0 or U11 is equals to U22 is equals to UNN is equals to 0. All are 0. So in this case, we want to find out what will be the steady state. So at steady state, the derivative is 0. So steady state S is equals to S approaches 0. Same as single unit isolated system, we have delta PGSS is equals to delta minus delta FSS divided by R. So let me just connect the battery. Okay, let us. So here delta delta PG1 steady state. It is same as single unit. For each unit, this will be same, only replaced by the particular generator's speed regulation characteristic Rn. And we also know that delta Pg1 steady state plus delta Pg2 steady state up to delta Pgn steady state minus delta PL is equals to this multiplied by Kp divided by 1 plus STP, and S is 0, so it is Kp. This is equals to delta S. This is coming from here, this one. We used just this part. By substituting S is equals to 1, we will get this. And if we replace delta Pg1 SS by this delta F by R1, so we will get, and Kp we can write Kp is equals to 1 by D. So Kp is 1 by D, so we can transfer D here. So delta F will, let us write it. It will be minus delta Fs divided by R1 minus delta Fss divided by R2, so on up to minus delta Fss divided by Rn minus delta PL is equals to D delta FSS. Okay, so delta FSS is equals to delta PL divided by D plus 1 by R1 plus 1 by R2 so on up to 1 by Rn, and this we can represent by 1 by R equivalent. So for the multi-unit system, this is the equivalent speed regulation characteristics. So we can write delta F is equals to minus delta F is plus 1, so it's equal minus 1 T plus 1 by R EQ, where R EQ is this. This is R EQ. So here we can see this is a uncontrolled mode, so there is a steady state error. So to eliminate this, load frequency control will use an integral control, integral or reset control. To restore the system frequency, to its nominal value. Okay. Now we'll see using this equation how parallel generators help us. Even without using control also, using parallel combination generator is very helpful. How we can see, let us see, if you assume that D is already very small, it is 1 by 120, let's say Kp is 120, so D is 1 by 120, so delta F, if we neglect D, it is minus delta PL divided by 1 by R1 plus 1 by R2 so on up to 1 by Rn. And also if we assume, so here we are saying D is almost 0 and R1 is equals to R2 up to Rn is equals to R, let's say. So this will become minus delta PL into R divided by N. So you see, if N is equals to 1, that means only one generator, then it is delta PL by R. And if we increase the number of generator, delta F is reducing. So steady state error goes on reducing if the number of generator increases. So this is very good thing. It's very, so many generator operating parallel reduces the steady state error, and for thermal generator, integral controller is used with small gain settings. Also one important thing that to note, so here we are saying that integral control is used. We are saying in the, here we can see, so this, we are saying this is integral control. So this is U here, so this is delta F here, delta F, and this is X4 is U here. So U we are saying if we have more than one generator, so here we have more. Delta F is 1, but we have these different U11, U22 up to UNN. So we can write delta F, then if we have a controller, integral controller, after this minus K by S, this is U, and this U is divided among different generators, so up to N. So it is A1, U11, A2, This is U22 and this is up to this is UNM. So how this U will be divided among these? And we have already seen that in steady state U is equals to delta Pg. U is equals to delta Pd. The amount of load which is changing, same the generation is also need to be changed. So how this delta PD will be divided among different generators, and this is based upon the participation factor. We already know that delta Pg 1 SS is equals to where A1 A2 up to AN are called the participation factor. Summation of A1 AI we can say it is equals to 1. I is equals to 1 to n. Summation of AI is equals to 1. So participation factors. So Pg11 is A1 into delta PL. So on up to Pg NSS is equals to An into delta PL. So load is divided, load is shared, it, and it is proportionate to the unit's rating. So this was for the single area system. Now after this we went into the concept of control area and then area control error and all that thing in the next week. So that what we studied up to here was for a single area, but actually entire system is divided into number of small areas. We can say, for example, the Indian power grid. We have five regions. Five regions. We have northern regions, we have western region, we have southern region, we have northeastern region and eastern region. So all these are five regions. So we can say these are five areas. So this entire India is divided into five areas, and we have tie lines between each of these regions connecting each other, and that's how we have one synchronous grid. So simultaneously, each control area of a power system should participate in regulating the frequency, and these areas are connected together by the tie line. So for load frequency control of a two area interconnected power system, we have in that same block which we have been using control block, we will add one more thing, that is the tie line in two areas. So block for both the areas will be similar. Only thing additional will be this tie line. So we have to model this tie line also. So P tie, we can say P tie 1 to flow is in this direction from 1 to 2. PR1 is the rating of generator in area 1 and here area 2. So for transmission system we assume that the resistance is negligible, and here what we can say, we want to see how a small change in load here in one of the area will affect things. Let us say this is bus 1, this is bus 2, and we have loads here, and this is I12, this is V2 angle delta 2 0 and V1 angle delta 1 0. So this is Initially, this much, let's say, power was flowing P tie 1 to 0 plus J Q tie 1 to 0. This was initially this much power was flowing over the tie line from 1 to 2. If there is a small change in load, how this will result in change in P tie and Q tie. So this we want to study, and this we can do linearization of this one linear equation by to know how much change will be there. So whenever we want to study small perturbation around a point, then we can do a linearization, first order Taylor series expansion. So we can see, or we can directly can uh, we can understand that using perturbation theory. So we can just give a small perturbation and then linearize it. So here we can write I12 is equals to V1 minus V2 divided by J x12. And V1 we know that V1 it is V1 angle delta 1 0 minus V2 angle delta 2 0 divided by J x12. Now we can write this V1, then so this is current, so power will be, we know that Vi conjugate is equals to P plus JQ. So we can also write it as V star V conjugate I is equals to P minus JQ. So we'll use the same thing here. Let me add one page. Insert page. Yes. So saying we will use that P minus JQ, or let's say here we are using P tie 120, P tie 12 initial minus J Q tie 12 initial, and this is equals to V1 conjugate V1 angle minus delta 10 multiplied by I12, and I12 we have already calculated V1 angle delta 10 minus V2 angle delta 20 divided by Jx12. So finally, I will not solve it. You can do it, and you can multiply it and then split it into sine and cos. Then on both the side equate the real and imaginary part. Finally, you will get P tie 12 is equals to V1 V2 sine delta 1 minus delta 20 divided by x1 x2. So this is initially what is happening. Now if we assume that we have a load disturbance in either of the areas or in both of them, then what will happen? Delta 10 and delta 20 will change, and the P tie 12 will deviate from its actual value. Let us say that the new values are delta 1, delta 2 and P tie 12. So let's say new values after a small load perturbation. We can write P tie 12 new value is equals to V1 V2 by x12 sine delta 1 minus delta 2. So these are the new values, and we also know that delta 1 is equals to delta 0. Delta 1 is equal to delta 1 0 plus delta 1. Similarly, delta 2 is equals to delta 2 0 plus delta 2, and P tie 1 2 is equals to P tie 0 1 2 plus delta p type 1 2. So we can substitute all these values here. So here after substituting and simplifying and assuming, because all these perturbations are very small, so we can say that sine of del sorry, when we will expand the sine terms, then we will get terms like this: sine of delta 1 minus delta 2, and cos of delta 1 minus delta 2. We know that for small angles, sine is equals to sine delta is equals to delta, and cos delta is equals to 1. So after substituting all this, we will get finally delta p type 1 2 is equals to v1 v2 cos of delta 1 0 minus delta 2 0 divided by p r1 x12 into delta x minus delta 1 minus delta 2, and this we can call as t12. And so delta p type 1 2 can also be written as 2 pi p12 into integral of delta f1 dt minus integral delta f2 dt. Because this angle, these are angle, but we want frequency, and we know that delta is equals to omega is equals to 2 pi f, because omega is d delta by dt. So we can replace delta by integral of 2 pi ft dt. Okay. So where delta 1, delta f1 and delta f2 are frequency deviation in both the areas. So if we take, so if we write del p phi 1 2 divided by delta p phi 2 1, then it will be minus p r2 divided by p r1, and this is 1 by a12. So a12 is equals to minus p r1 divided by p r2. This we call as area capacity ratio. PR1 is the capacity of generator in area 1, and PR2 is the capacity of generator in area 2. So you can say P type 1, P type 21 is equals to A12 times P type 12. So now we already know the equation, that in steady state we can write this equation: P delta Pg1 minus delta PL1. So this is for area 1 minus delta P type 1 2 is equals to 2h upon f naught d by dt of delta f1 plus d1 delta f1. And after taking Laplace transform, we will find this delta Pg1 minus delta PL1 minus delta P type 1 2 multiplied by Kp1 divided by 1 plus STP1, where Kp1 is equals to 1 by d1 and Tp1 is equals to 2h1 divided by d1 f0. So for tie line, we will find this type of diagram. Earlier we were having delta Pg2 and here only delta minus delta PL. But now here we have A12 negative, this is minus delta PL, and this is delta P tie 12. and here we will be having Kp upon 1 plus S T2 Tp2. So this is for second area. For area 1 it will A12 will not be there, it will be delta beta E12. This will minus delta PL1 PL2 PL1 for area 1. And for for delta P tie we found P tie as 2 pi into, we saw here, no? 2 pi T12 into integral of delta F dt minus delta F2 dt. This, by taking Laplace, you can write it as integral is 1 by S. This is delta F1 minus delta F2. Delta P tie is having a transfer function like this representation like this. So similarly, just as we did it for multi-area input, so multi-unit isolated system, if we write the equation here for the entire diagram, then we will find that steady state deviation into area at steady state, it will be 0 for, so for uncontrolled system it will be delta F1 and delta F2 will be equals to some delta F steady state. In steady state, frequency deviation in both the areas will be same, and delta P G steady state tie 1 2 minus delta PL1. So this same equation. In steady state, this part is 0 in steady state, and we are left with only this one. So this will be d1 into delta F steady state. Similarly, for second area also, Pg2 steady state minus delta P steady state I 1 2 minus delta PL2 is equals to d2 into delta F SS. And from isolated system, we already know that Pg1 SS is equals to minus delta F SS divided by R1. And for second area, it will be minus delta F SS divided by R2. If we substitute this here, these two values in these two equations, then we will have two equations, and after solving the equations, we will find that delta F SS is equals to A12 into delta PL1 minus delta PL2 divided by D1 D2 plus 1 by R2 minus A12 into D1 plus 1 by R1. Similarly, delta P tie will be equals to D1 plus 1 by R1 into delta PL2 minus D2 plus 1 by R2 into delta PL1 divided by denominator is same, A12 into D1 plus 1 by R1. Now here also, if we assume that there is deviation in only area 2, that means PL2 is 0, is only delta PL1, and so delta FSS will be A12 delta PL1 divided by D2 plus 1 by R2 minus A12 D1 plus 1 by R1. Similarly, delta P tie is equals to minus D2 plus 1 by R2 into delta PL1 divided by D2 plus 1 by R2 minus A12 D1 plus 1 by R1. Now here, if we assume for a special case, let's say for D1 is equals to D2 is equals to 0 and R1 is equals to R2 is equals to R. Let us calculate what will be delta F. So delta F SS in this case will be, so D2 0, D1 is 0, and one more thing, A12 is equals to minus 1. When will this happen? When PR1 is equals to PR2. The rating of generated in both the areas is same. So A12 becomes minus 1. So if this is 1, so this becomes A12 is minus. So this is minus delta P L1 upon 1 by R1 plus 1 by R2. So we see same which we saw for multi-unit isolated system. This is same as multi-unit isolated system. So for this to happen, for these are the requirements. So D1, D2, 0, and both speed regulation characteristic is same, and even the power capacity are also same. Then we will get the output delta F steady state, same as what we got for the multi-unit isolated system. And P tie, delta P tie will be, so D is 0, and this is minus 1 by R2 P delta PL1, this is 0. So this is minus delta PL1 divided by R, and this is 1 by R, this is 2 by R. This is minus delta PL1 divided by 2. Because there is no perturbation, no change in of load in area 2. So for this we have to remember that delta PL2 is also 0. So all these are the conditions 1, 2, 3 and 4. So all these 4 things, under these 4 conditions we will get delta F as same as the multi-unit isolated system. So after this, next week we will see the area control error. Area control error. So we'll just introduce it, area control error. And also we have already seen one thing, that this beta D plus 1 by R for an isolated system. This is called bias setting, frequency bias setting. So for 2 area it will be, for area 1 it is beta 1, D1 1 by R1. For second area it is beta 2, which is D2 plus 1 by R2. So it is frequency bias setting. So area control error ACE, it depends upon the two things. So changes in the Thailand power flow as well as the change in the frequency. And all these things, it's a combination of these two, and it happens because of the load imbalance in the areas. You can say area control error in area 1 is equals to beta 1, so this is beta 1 into delta F1 plus P tie 1 2, delta P tie 1 2, and ACE2 is equals to beta 2 delta F2 plus A12 delta P tie 1 2. Okay, so A12 is minus P R1 upon P R2. Both are same, then A12 is minus 1. So now these two is another, this also we have to model its transfer function and then add it into the control block and again write the equations. Then we will get final equation with control, without control mode, that we will see in the next week. So these are the some important things. Most important thing, the formula which you need to remember, which you will come across again and again, is one is you need to remember that beta. What is beta? Frequency bias setting for area 1 is D1 plus 1 by R1, and combined for two areas it will be beta 1 plus beta 2 And for a isolated system, you need to remember the delta FSS is equals to minus delta PL divided by this beta 1 by d plus 1 by r in q. Okay, so this is for multi-unit isolated system, and also for two area system under this condition which we have already referred here. This is an important uh, formula which you need to remember. And so now let us see some questions for this week. We'll start with the first question. And so this is the first question. The first question is, the area control error in a multi-area power system reflects what? So this we discussed in the last, no? In the last thing which we discussed today was this area control error, which is also the beginning of the next week. So area control error here, what does it reflect? We saw that it is a combination of two things. Area control error for one area is beta 1 into delta f1 plus delta p die 1 1 2. So it depends on the changes in the Thailand power flow and the changes in frequency, and it reflects the total load power imbalance. Because all this, only this load power imbalance results in this two things. Whenever there is load power balance, then there will be change in F1 in frequency of area 1, and also the Thailand power flow from area 1 to 2. So when so the primary control is the load frequency control, where we want to bring back the frequency to its nominal value. Suppose for the even the if after the primary control, even after using the integral control, the distance may be so large that the steady state error is not zero. That means the primary control is not able to restore the system frequency. So the nominal value. In that case, we need to go for the secondary control. Secondary control, and here we need to change change the power reference itself. We need to change the power reference. So this is all because of this load frequency control. Even if the secondary control is not able to do that, then we need to go to the tertiary control. And tertiary control is generally it's manual intervention. Yes, so in each area, the area control error reflects the power imbalance of the load, and the value of AC depends on changes in frequency and the Thailand power flow, as we have seen here. So it depends upon the change in frequency as well as the Thailand power flow, and it reflects the load power imbalance. Then the objective of secondary frequency control, this also we discussed that its objective is to change the reference frequency. This is the objective of the primary frequency, primary control. So now let us move to the numerical questions. So we'll see them very in detail, one by one. So you can ask any doubt if you have. So what is the this is the first question. A frequency sensitive load connected to a 60 Hz power system. So 60 Hz. Whenever you see a question, always, because sometimes we are in such a hurry that we don't even read the question correctly. In our mind, it is that we are accustomed to solving questions for 50 Hz. Indian power system is operating at 50 Hz, so we think that the question is also at 50 Hz, and we keep on. Without reading carefully the question, we assume that this is a 50 Hz system. So always, when the question is there, read the values very carefully, and also read what the question is asking. It's very important. But we, in a hurry, we make such mistakes and we might end up doing blunders. So here it is 60 Hz, not 50 Hz. Then next value is that the load connected to 60 Hz changes by 1.25. So load sensitivity factor we are going to find here. It's giving information about D. So changes by 1.25% for a 1% change in frequency. And also this is very important. So this is for a 500 kV system base. That means 0.5 MVA system base. So this D value given in the question is on 0.5 MVA system base. Now if the system base is changed to 1 MVA, what will be the value of D? That's the next question. What will be the value of T if the system base changes in per unit megawatt per hertz, where D is the frequency sensitive constant of load. Yeah, so let us see what is the value of D on the system base, on the old system base first. We know that per unit is equals to actual value, let's say per unit in some system 1, let's say, divided by the system base 1. Okay. Actual value will not change, right? If I take another system base, then per unit value will change. The actual value will not change. A resistance of 5 ohm will remain a 5 ohm resistance whether we take a base on a different two different systems. Only thing here will the system base and per unit values will change. So you can say if we equate these two, what we will get PU1 into system base. I am writing it as SB. System base 1 is equals to PU2 into system base 2 SB2. And if you want to find out PU2, so we can write PU1 into SB1, system base 1 divided by system base 2. Okay. So now we need to first find out. So finally we have to find the value of D in per unit megawatt per hertz in the system base 2. So for that we need to find what is the value in the system base 1. So here we see D is given as 1.25% change or 1% change in frequency. So this is 1.25% change in load. Divided by change frequency. 1% of 60. And this is 1.5% of 0.5. So this is per unit value in the system 1. D per unit value in system base 1. So now we need to use this. So per unit into SB1 divided by SB2. System base 1 is 0.5 and system base 2 is 1. This will get per unit values in the system base 2. So this will be 1.25 divided by 100 multiplied by 0.5 1 divided by 100 into 60. So this will be how much? 1.25 multiplied by 0.5 divided by 60. So this is 1 by 96 per unit megawatts per hertz. Okay. This is 1 by 96. 1 by 96 comes out to 0.01042. Okay. Yeah, so next, let us, so same thing is written here also. Let us move to the next question. So here, no, this is, none of the option is correct because the actual answer is 0.01042. So divide by this by 10. That is the actual answer. So answer is none of the above. Then let us go to the next question. So next question is a 60 hertz small system consists of 5. So again, see this is 60 hertz. Note it. Down. Then you have to say this is 5 identical 400 kV generator feeding a total load of 1 megawatt. Total load is inertia constant of each unit is 6.01 500 kV base. Okay. 6, and then total load varies by 10% or 1% change in frequency. This is giving us information of D. Speed regulation R is given as 1.0 hertz, 1 hertz per unit megawatt. So when there is a sudden increase in load of 100 megawatts, that is equals to 0.1 megawatt. You have to find out the steady state frequency. Assuming there is the speed governor is in it. That means 1 by R. We have to assume that there is no governor. That means you have to only consider the effect of D, the load sensitivity. So here, what first of all you have to find what is the system base MBA. So system base MBA here is so initially the generation, since load is 1 megawatt, so system base, so this is M1 MBA. So new system base is equals to, it is 5 times, 5 generators are there, 5 into 400 their capacity divided by 1000, earlier value, which so it comes out to be 2 per unit, 2 MVA, system base 2 MVA. Then system load, increase in load, so earlier it was 1, now it is 0.1, it becomes 1.1 megawatt now. So we have to find the W parameter. D is equals to 0.10% divided by 1% change in frequency. So this is 10 into 10% of 1.1 and 1% of 60. So this is 10 into 1.1 divided by 60. 10 into 1.1 divided by 60. So this is 0.1833. It is in megawatts. 80 megawatts per hertz. This is not in per unit. If you want to find out it in per unit, then we have to again divide it by the system base. So when the speed, we have seen that delta FSS. I told you that we have only that formula, that PL, it is minus delta PL divided by D plus 1 by R EQ. This is an isolated small system, isolated system with 5 generators. So REQ we have already find out. So, but REQ is not there here because there is no speed governor. So it is only D, so it is minus delta PL divided by D itself. So this is a very simple question. So if we find steady state frequency error, this is equals to minus delta PL divided by D. What is delta PL? Delta PL is 0.1 divided by D is 0.18333. So this is megawatt, this is megawatt. It will give you output in hertz. So this much change in hertz. What do I find one? So this is minus. So when there is an increase in load, so frequency will reduce. This is showing that frequency will reduce by 0.545454. It's a recurring. So this is the steady state frequency error. So increasing the load is increasing, so steady state, so the frequency will reduce because the steady state frequency deviation is negative. So this is the first part of the question where we are not considering the speed governor. We are considering that it is inactive. So because it is inactive, there will be more deviation in frequency from its initial value. But when we incorporate the speed governor within it, then we will see that the frequency deviation will reduce. And that is the next part of the question. So first part of the question we have already solved here, and we found that the deviation in the frequency or the steady state frequency deviation is, it comes out to be minus 0.54. So new frequency, we can say new steady state frequency is equals to old frequency minus delta f. So sorry, plus delta f, and delta f here is negative. So it is 60 minus 0.545454. So this is 59.4545 hertz. So 45, which answer is correct here? 45 means this one. D answer is correct here. The same is done here also. Yeah. So now the same question we see here. Now we have to consider the speed governor also. All the parameters are same because it is the second part, continuation of the same question. 5 identical 400 kVA generating units feeding a total load of 1 megawatt. Inertial constant of each unit is 6 on 500 kVA base, and the total load varies by 10% for 1% change in frequency, and speed regulation characteristics is 1 hertz per unit megawatt, and there is a sudden increase in load of 100 megawatts. So what is the percentage improvement in the steady state frequency obtained after activating this speed governor loop? So here we see R is given as 1.0 hertz per unit megawatt. Okay, speed regulation and so because everything D we have calculated in megawatt per hertz. Let us convert this into its actual value. So we need to multiply it by the system base. And what was the system base? Where is the system base? It is 1 hertz. Total we have 5 units. We have found here the system basis 2 MVA. We know it is delta P because this is in per unit, so we need to multiply this by its base value. So actually we are dividing R by the base value because in delta P is coming in denominator in R. So system base we have already calculated in the previous part. The system base is equals to 5 into 200 divided by 1000, which is 2 MVA. Okay, so R is equals to 1 per unit hertz divided by per unit. You have to convert it into actual value. The actual value, so we have to multiply it by the system base. And system base is 2 MVA. So it will come out to be hertz by per unit is gone now. This become zero point 0.5 hertz per megahertz. So this is the actual value of R on the new system base. So now we need to find out the frequency uh, delta F. So delta F steady state in this case is minus delta P, same dy 1 by R, and so this is minus 0.1, and d we found earlier also 0.1833. So it is 10 into 1.1 divided by 60. This is 11 by 60 plus 1 divided by 2. plus 0.5 in it is 6. So this is 2. This should be 2. Then my 60 plus 2. Inverse multiplied by minus 20. So 6 by 131. This is minus 6 by 131. And this comes up to minus 0.0450 So we see here, we compare the both part 1 and part 2. Here we found delta FSS to be minus 0.54. And here it is minus 0.045. So this is very less. We see including the speed governor loop benefits us so much. So there is a lot of improvement in the frequency here. And we need to find how much frequency is improved here. So this is the new frequency in this case. Let's say frequency 2 here is F plus delta F steady state. This is 60 minus 0.03802 and this is equals to, we add 60 here, this is 59.9541. So now we need to find the percentage improvement. So it will be 59.9541 minus 59.4545 divided by 59.4545. Multiplied by 100. And this into multiplied by 100. So this is 0.8405%. So answer A is correct here. So this is F2 and this was F1. So here it's clear, right? By using the speed governor loop, we are able to increase the final value of frequency, or we can say we are able to reduce the frequency deviation. Yeah, same thing is explained here. Let me write it here. One thing that the system base here is 2 MVA. 2 MVA. Now let us move to the next question. So this is the next question here. This is the sixth question. So the speed regulation characteristics of two generators connected in a power system. So we have one power system. We can say that this is multi-unit isolated power system. It's a multi-unit isolated power system with two generators. The generator 1 is having this specification is 100 MVA 50 Hz, both are 50 Hz, are 1.02 Hz per unit megawatt on machine base. So again, we have to use we have to convert it into with two equivalent and so system base is this 100 MVA. So this is already given in hertz per megawatt, and we need to find out in per unit. So we need to convert either you can do it anyway. Either first convert it into actual value, and then find the overall actual value, and then convert the actual value into per unit, or you convert this into actual value, this into per unit value, and then find out the overall per unit value. So whatever way you want, you can do it. So this both are based on machine base, and machine base of this is same as system base, but for generator 2 the machine base is different. So let us, to make it easier, what we can do, find out the actual value of generator 1 first. So it is similar to what we did in the previous question, because we saw that we know that R is this delta F by delta P, that is why it is in megawatt, sorry, hertz per megawatt. It is in hertz per megawatt. Now, if we want to, this is actual value, and we want to convert it to per unit, then what are we going to do? We have to delta P, we need to divide it by the system base. So then it becomes per unit megawatt. So here, what is the system base here? System base is 100 MVA. Machine base is also 100 MVA. So we just need to multiply it by 100 to convert it into actual value. So let us say if this is in hertz per unit megawatt, then what we need to do? So this is R1 in per unit. So R1 actual will be delta F multiplied divided by delta P into system base, and this will be hertz per megawatt. So R1 here, actual value will be 0.02 hertz per unit megawatt divided by system base, which is 100. So how much is this? So this is 0.0002 hertz per megawatt. This is actual value. So this is the actual value, and R2 in actual value for R2 is 0.005 hertz per megawatt. So we know that Req, 1 by Req is equals to 1 by R1 plus 1 by R2. Same as we have what we have if we have resistor or impedances in parallel. This is R1, this is R2, then R equivalent is equals to R1 R2 divided by R1 plus R2. Same thing here, we can, it is similar. All these two things are different, but yes, it is similar kind of formula here also. Sorry, we can write it R2. So this is 0.0002 multiplied by 0.005 divided by 0.0052. So how much is this? Let us find out. 0.005 divided by 0.052. So this is 0.001923. This is in hertz per megawatt. Now if you want to find out per unit, then you need to multiply it by system base. So this one is Req, and Req per unit is equals to Req into 100. So this will be 0.01923 hertz per unit megawatt. Okay. So what is, we are asked to calculate the equivalent speed regulation in hertz per unit megawatt. So this is correct. 0.019 per unit hertz, hertz per unit megawatt. So this will be the correct answer. Yeah, so same thing is explained here also. So most important thing is this one, this conversion into the base value. Suppose we want to do it other way, that we want to first calculate the per unit of this, then how are you going to do that? So we have already seen that per unit value in system in base 1 multiplied by system base 1 is equals to per unit in system base 2 multiplied by system base 2. And here we want to find out per unit in, sorry, want to find out the per unit into, then it will be per unit 1 into system base 1, which is equals to the actual value divided by system base 2. So actual value we already know here. This is 0.005. Actually, this is valid when we're doing something like this. Let P of, let's say, per unit of value is equals to actual value divided by its base value. But here what is happening are it is delta by delta P, and we want to convert this into per unit. So actually this is in denominator. So it is actually per unit here is equals to available actual value into system base. So things will change here. Here per unit R per unit 1 divided by system base 1 is equals to R per unit 2 divided by system base 2. You need to find out the R per unit divided 2. So which is actual value, because this is actual value in system. This is actual value. This is R. Then multiply it with system base 2. Remove. Okay, so this is R into system base 2. What is R is 0.005. System base 2 is 100. This is point. This is 0.5. This 0.5. So again, can you see? Let me do it here. It will be 1 by, so RQ is equals to R2 plus 1R2, and this is given as 0.02 into 0.5 divided by 0.02 plus 0.5. This is 1 by 52, which is same as 0.0123. And same thing, so both way you can do it anyway. So this is in hertz per unit megawatts. So either first convert this into per unit and then take R equivalent, which will give you directly R equivalent in the per unit, or second way which we did first is first convert this into actual value and then take the REQ and then find the per unit value in the new system base. Both way will get the same answer. So you can do both ways. So this is right. This is method one, and this is method two. So here, let me write it here. R two on R R two per unit two is equals to R two. So let me write to be R two into system base two, which is equals to 0.005 multiplied by 100. This is 0.5 volts per megawatt. And first one is already given in hertz. So this is hertz per unit megawatt. And R1 is already given in per unit. And this is on the same. And initial base and both the bases are same. This is 0.02 hertz per unit megawatt. So both way you can do this question. So let us move to the next question. This question also has two parts. Yeah, two parts. So consider a two-area system connected. It's a two-area system. We have area 1 connected by a tie line. This is area 2 and this is the tie line. So P tie 1 2 with the lossless tie line with the speed regulation R1, that is right. R1 is 0.03 per unit and R2 is 0.045 per unit. That means it is in hertz per unit megawatt, and damping factor is zero point 0.9 per unit megawatt per unit, and D2 is 0.6 per unit. Base, yeah, system base is same. Initial base is also 100 MVA for both the areas. Now area 1 is subjected to a load increment of 9 megawatts. So delta PL1 is equals to 100. So it is 9 divided by 100, which is 0.09 per unit. Delta 1 is subjected to a load increment. So delta PL1 is 0.09 per unit. फोटो किसने इसने लिखा and delta PL2 is equals to 12.5 megawatt divided by 100. This is 0.25 per unit. Let me check one thing here. Such area is subjected to load increment or decrement. Is this increment or decrement? Yes, I need to check.
एक 100 रुपये का है या तो मूल दर्शन की ले सकते हैं तो लाइन में थोड़ा टाइम लगता है बाकी अगर इसमें जाए तो पड़ी इसलिए टाइम लगेगा
Well, maybe.
अरे वो तो ना मैं तो बोलता हूँ मैं सर को बोल रहा था मैं कोई भी कॉलेज में जाओ तो वो रहता है और रिलायंस में जाओ तो वहाँ रहेगा टाटा पावर में जाओ तो वहाँ रहेगा कोई किसी के साथ नहीं बोलता है यार अप्रोच जाती है कोई भी क्लाइंट हो तो कोई बोलता है अच्छा हम गए उसके बाद मैं और मेरे पास कुछ है तो दे दो ना उधर के इधर ही हो जाएगा फिर उनको पूछो ये वो तो कुछ भी कैसे भी फॉर्मेट में हो तो दे दो इतना चलेगा हार्ड कॉपी चलेगा सॉफ्ट कॉपी कुछ भी है तो दे दो हाँ देता हूँ कल देता हूँ बोलते आज कुछ नहीं
The load should be decremented. Increments. Increments is positive or negative?
हाँ वो तो मेरे को भी बोला
फिर पता चला कि इसकी लैब है
So this is built up here. Yes. Positive. It's 50 minutes. Okay. Yes, we need to find out D. So delta data is so D1 is 0.5, D2 is 0.6, R1 is 0.03, D2 is 0.045, beta is 57.05. So this is the same formula is here. This only we have to use because here A12 is equals to -1 as PR1 is equals to PR2. If we substitute A12 as -1, okay, let me copy this. Yes. Yes, we are using this formula only. And here A12 is equals to minus 1 because both the system rating are same. Okay. So A12 is minus 1 here. So this becomes minus 1. So minus. That is why it is delta F plus is compared to minus delta PL1 plus delta PL2. And this is beta, which is this D1 plus D2. And delta beta, which is the next point. Delta beta will become D1. So this will also become this will become
सर ये ओके हमको भी देखने कितना टाइम है क्या कर रहा है
this will become D1 plus by R1 into delta
आगे सर कर दिया गया
minus D2 plus
मैथ मार गया
by RT.
ये बड़ी प्रॉब्लम है सर कि काम कर रहे हैं
बहुत बड़ा
This
प्रॉब्लम है
is beta here.
दाल फ्राई खा रहे हैं
This
दाल
will
ये अभी
become
चटोरी दाल कर दो
delta PL1 is
मेरा पास करने खा जा
0.09 minus 0.09 plus
नहीं शाम को नहीं खाऊं
0.125
अब आपने कब रात को बोला आपने तो बोला
divided
बेटर है गेम में बट आई एम नॉट मतलब एक्सपर्ट मैंने सुना है एक्चुअली द क्वालिटी ऑफ इंटरव्यूज इज बेटर
by is
ड्यूरिंग द सन व्हेन द सन इज अप उसी जनरेशन सर ये बस आई विल आते नहीं अगर उसके मैं इवन जी में एक्सपर्ट नहीं हूँ मैं क्लेम नहीं करता आई एम एक्सपर्ट आई नो व्हाट वर्क्स फॉर मी जी में एक्सपर्ट आई नो व्हाट एक्सपर्ट वर्क्स फॉर मी एंड आई एम नॉट श्योर इज इट ऑप्टिमल और नॉट बहुत से बेटर वे में कुछ हो सकता है बट डिस्क्लेमर हम बच्चे रहते हैं आई एम नॉट एक्सपर्ट डू योर ओन रीडिंग
लेकिन एडवाइस तो करता है
एडवाइस कर सकता हूँ डिस्क्लेमर सर
नहीं उसको नहीं डाल उसमें कैसे बोलते हैं कि नहीं आप ये करो देखो होगा
यूट्यूब पे तो एक्सप्रेसेस कुछ भी बोल सकते हैं सब लोग बताते हैं एंड वो नॉट सर्टिफाइड
converts actual value will be 0.036806 watts.
तो गलत किया
This is delta F. This is steady state frequency deviation.
ये चैनल शिफ्ट चल रही है चैनल ये
तो आप मूवी के बाद सब कुछ
नहीं नहीं
This is the steady state frequency deviation. Now we can use this same formula here also. And we can write D1 is 0.9 plus 1 by R is 0.03. Delta PL2 is 0.125 minus D2 is 0.6 plus 1 by 0.045 minus 0.09 divided by 57.05. Just calculate this. 0.9 plus P inverse plus point. This comes out to be 0.11100001 per unit. And multiplied by 100 if you get 11.1 megawatt. So this will be in megawatts per unit and megawatts. So we have to use this formula only. So this is for two area system, and because here we have built this A12 here A12 is equals to -1. So from here we can write this by substituting A12 is -1. This also we get by substituting A12 as -1. So here we can write A12 as -1. So this becomes beta. Overall beta, which is D1 plus D2 plus 1 by R1 plus 1 by R2. Now let us move to the next question. So this is same part. And this is done using another method. This also you can do. So here what is done? Here delta. This uses the equation that delta Pg minus delta PL1 minus delta P Ti12 is equals to D1 into delta F. All these things we already know. Okay, because delta F we have already found in the part 1. So from here we can find out delta Pg. And so delta Pg also we know that delta Pg is also one more equation is delta F divided by R1. This also we know. So we can substitute it here and then we can find out P Ti12. Right? Substitute this over here. Substitute this here. So this becomes minus delta F1 and delta F divided by R1. From here also you can find out the P Ti1. So same thing is used here. P Ti12 becomes, so here delta P Ti12 becomes this goes here, so it becomes minus delta F by R1 minus delta PL1 minus T1 delta F. Okay, because F is negative, no? Delta F is negative. Delta F is negative here. This is negative. So this is negative. So this will become negative. This will become positive. Then so same. So this is method 2. Actually both the methods are same only because we have received these equations. After substituting that only we have solved this. So you can use any of these two methods. In second one is more beneficial because here you no need to remember the formula for delta F steady state and delta P Ti. No need to remember the formula. You need to remember these two equations. Also delta F you need to remember. Means anyway you can find out if you write these two equations for both the areas and also write this equation that delta Pg is equals to minus delta F by R. Then solve these 4 equations and you will get the answer. So no need to remember the formula. Now let us move to the last 2 questions. This is the 9th and the continuation is also 10th. So same question. This question also has 2 parts. So this is question 9. Figure for question 9. It is observed that delta PL. So this is delta PL. Delta PL is minus 0.15 per unit and this delta brings about a delta omega change in frequency of 0.25 per unit. In steady state, so delta W steady state is given as 0.25 per unit. and delta PL is given as minus 0.15 per unit. So we have to find out the value of R. So take delta, sorry, this is not delta PL, this should be delta PC. This is delta PC. So delta PC we are taking here as 0. So we can simply write these equations. What is this? So this is delta W here. So this is 0, this is multiplied by minus delta omega by R into 1 by S plus 1. This is plus minus delta PL, sorry, and this is whole multiplied by 10 divided by 1 plus, sorry, 10s plus 1. This is 10s plus 1, and this is equals to delta omega. So from here we need to find out the delta omega. In delta omega we know, but we need to calculate the delta P R value from here, this R value. So we need to simplify it first, find out the value of delta omega here. So what we can do, we can write delta omega R S plus 1. This is equal to delta omega into 10s plus 1 divided by 10. Oh, I made some mistake. Yes, this is minus delta PL also. Let me write it on the other page. Let me add one page here. Keep it. Let me copy this figure. So it's a good question. It's not that difficult, but yes, it's a nice question. So let me add one page here. Okay. Yeah. So we have this diagram here. Sorry. Okay. Insert, not insert, lasso. Just move it a bit up to here. Yeah. So okay, let me go to the full screen mode. Okay, yes. So what was I saying here? Yes. So first of all, first important, yes. Yeah. So delta PC we are taking it as 0. So minus delta W delta omega by R multiplied by 1 by S plus 1 minus delta PL, and this is to be multiplied by 10 divided by 10s plus 1, and this is also equals to delta omega. So what we can write, this is delta omega into, say, subsume minus 1 here, 1 by R into S plus 1 into 10 divided by 10s. So this is 10 divided by 1 plus 10s. And this is minus delta PL divided by into 10 divided by 10s plus 1, and this is equals to delta omega. Now delta omega is equals to 1 plus 10 divided by 1 plus 10s into R into S plus 1, and this is equals to minus delta PL into 10 divided by 1 plus 10s. Have I made some mistake? I think everything is fine, under control. Yes. Yes. So delta omega comes out to be minus 10 divided by 10 plus 10s plus 1 divided by 1 plus 10 divided by 10s plus 1 into S plus 1 R and into delta PL. Now we have been given the value of delta omega to be how much? Delta omega is 0.25. So substitute the values 0.25, and what is delta PL is minus 0.15. And sorry, for steady state, first of all, this is delta omega, so delta omega steady state is equal to limit as tends to 0 delta omega, because in steady state all the derivatives are 0, so as goes to 0. So this becomes 0.25. Delta omega steady state is 0.25, right? And so substitute s is equals to 0, this is 0, so this is minus 10 divided by 1 plus, this is 0, this is 10 by r, and this is minus 0.15. Okay, so this is 1 plus 10 divided by r is equals to 10 into 0.15 divided by 0.25. So 10 into 0.15 divided by 0.25. So this is 6. So 10 by r,
इसे पता है एक तो एलिमेंट मॉडल तो ये तो यहाँ पे है मतलब जो मतलब ये है ना एलिमेंट आज वो ये कंप्लीट शट डाउन आज तुझे पता है मुझे कुछ समझ में आया
so this is plus 10 is equals to 10 into 0.15 divided by 0.25. This is 6. So 10 by r is equals to 5. This implies r is equals to 2 per unit. Yes. So this is now next question. Same continuation of this. Here in this question, what is this? For isolated system with local mode, delta is equals to PL1. Find the, no, so this is not R, actually this is delta PC. We need to find out the delta PC now. We have to consider delta PC here also, and R we already found out. This is R is 2 per unit. So again we need to write this thing. So we can write out, let me again add one page here. Or let me just show it here, because it is already done here. So you can see here, so this delta omega, just let me add the image here, at least you can see how is that written. Yeah, so here you see this is delta W comes out to be delta W is equal to this. First take this PC minus delta omega by R. So this is delta PC minus delta omega by R multiplied by 1 plus S minus delta PL multiplied by this. So finally we will get delta omega is equals to this. And here our steady state, we already know that it is written that steady state omega is here is actually it is 0 here. So I will change this question. This is not delta omega has to be 0 here in steady state, and we have to find out the value of delta PC. So if you apply limit s tends to 0 delta omega, this is 0, and this in this, if it is this is 0, then delta PC is equals to delta PL. And we already know that delta means U in steady state is always equal to delta PL, which is, so that's why here we find that PC delta PC is equals to delta PL, and because delta PC is here, this is the U only, so which is same as minus 0.15, which is delta PL itself. So this is also done. I will change the question. There is a mistake here in the question that I will change. So, but thank you all of you for joining today's class, and we will meet next time, next Saturday, same time. Thank you very much.